There is a telescope in Chile that does not sleep. Every night, high in the Atacama Desert, it opens the largest digital camera ever built and stares into the dark. But it does not look at the universe the way other telescopes do. It does not choose one galaxy and study it for weeks. It does not wait for one perfect image. It does not capture space as a frozen picture. It watches everything, again and again. Every 3 nights, the Vera Rubin Observatory scans the visible southern sky, searching for anything that moved, brightened, vanished, exploded, or appeared where nothing was supposed to be. And in its first months, before its full mission had even truly begun, it started finding things that should not have been there. A single image containing 10 million galaxies. A river of stars stretching 163,000 light-years from a spiral galaxy. More than 11,000 newly discovered asteroids. A spinning object so large and rotating so fast that physics says it should have torn itself apart. A star in Andromeda that may have collapsed directly into darkness. And objects from other star systems passing silently through ours, like visitors from places we will never reach. Rubin was built to map the universe. But what it captured first was something far more disturbing. Proof that the sky is changing faster than we can understand it. The Vera Rubin Observatory sits on a mountain in Chile beneath some of the driest and darkest skies on Earth. Mission is called the Legacy Survey of Space and Time. That name sounds calm, almost academic. But what it really means is this. Rubin is building a 10-year movie of the universe, not a picture. A movie. Every few nights it scans the entire visible sky from the southern hemisphere. Then it compares the new image with the last one. If something has changed, Rubin notices. A dot moved. A star dimmed. A galaxy flared. An asteroid appeared. Something vanished. And each change becomes an alert. When Rubin's alert system was tested, it produced hundreds of thousands of alerts in a single night. Eventually, the observatory is expected to generate millions of alerts every night. Each one pointing to something in the sky that is different from before. This is what makes Rubin unlike almost every telescope humanity has ever built. Hubble changed astronomy by showing us detail. James Webb changed astronomy by showing us infrared light from the ancient universe. But Rubin is different. Rubin changes astronomy by giving the sky memory. For thousands of years, humans looked up and saw patterns. Stars seemed fixed. Constellations appeared eternal. Galaxies looked distant and silent. The universe felt slow, almost frozen. But Rubin is revealing that this was an illusion. The sky is alive with motion. Asteroids cross the solar system. Stars explode. Black holes may form without warning. Objects from other star systems enter and leave. Galaxies stretch, tear, merge, and reveal structures too faint for older surveys to see. And because Rubin keeps returning to the same places, it can detect changes that no single image could ever reveal. This is the new frontier, not just deep space, changing space. And the first results already showed how much we had been missing. On June 23, 2025, the world saw the first images from Rubin, and one of them was almost impossible to process. A single composite image of the Virgo cluster contained around 10 million galaxies. 10 million galaxies. Not stars. Galaxies. Each one potentially holding billions of stars, planets, black holes, nebulae, and unknown worlds. And this was just one image, covering only a tiny fraction of what Rubin will eventually photograph. If you tried to look at every galaxy in that one image for only 1 second each, without stopping, without sleeping, without blinking through the task, it would take you months. And yet for Rubin, that was only the beginning. The telescope is expected to observe billions of galaxies over its decade-long survey, creating one of the most complete maps of the universe ever assembled. But buried inside those early images was something more unexpected. A stellar stream, a river of stars being pulled away from the spiral galaxy. Messier 61. It stretched 163,000 light-years. That is larger than the diameter of the Milky Way, and no one knew it was there. This is one of the reasons Rubin is so powerful. It does not only detect bright, obvious objects, it can reveal faint structures spread across enormous areas of sky, structures too wide, too dim, or too subtle for other telescopes to easily capture. A stellar stream is not just a beautiful feature. It is evidence of violence. It means gravity is tearing a system apart. A smaller galaxy or star cluster may have passed too close to a larger galaxy, and now its stars are being stretched into a long cosmic river. These streams are the fossil trails of galactic destruction. They show how galaxies grow, how they devour smaller systems, how invisible dark matter shapes the motion of stars, and how the universe builds large structures through collision, gravity, and time. Rubin captured one that had been hiding in plain sight. A structure larger than our galaxy, invisible until the right instrument looked with enough width, enough sensitivity, and enough patience, and that was only one of the first surprises. Before its full mission even began, Rubin discovered more than 11,000 new asteroids. That alone would be historic, but it is only a preview. Scientists expect Rubin to discover around 1 million previously unknown asteroids in its first year of full operation, roughly equal to the number humanity has catalogued over the previous 2 centuries. In 12 months, Rubin could double centuries of asteroid discovery. That matters because asteroids are not just rocks. They are remnants of the early solar system. They carry records of planetary formation, collisions, migration, and the violent history of the space around Earth. Some are harmless. Some cross near our planet. Some may become important for future missions. And some are strange enough to challenge what we think we know. One of them is called 2025 MN45. It is enormous, almost twice the height of the Empire State Building. But its size is not what makes it so disturbing. Its rotation is. This object is spinning once every 1 minute and 53 seconds. For something that large, that is extremely fast. Fast enough that centrifugal force should be pulling it apart. A rubble pile asteroid rotating that quickly should not remain intact. It should shed material. It should stretch, fracture, or disintegrate into debris, but 2025 MN45 is still there, still spinning, still holding together. Maybe it is not a loose rubble pile. Maybe it has unusual internal strength. Maybe its composition is different from what we expect. Maybe some process shaped it in a way we have not yet modeled. But the deeper point is this. Rubin is not just finding more objects. It is finding objects that force better questions, and asteroids are only one category. Rubin may also become one of the greatest tools ever built for detecting interstellar visitors. In all of recorded history, humanity has confirmed only a few objects that came from outside our solar system and passed through ours. Oumuamua was the most famous, partly because of its strange shape, trajectory, and unexpected acceleration. Then came other interstellar objects, each one a messenger from another star system. Rubin is expected to find more, maybe 5, maybe dozens, maybe hundreds. Objects from places we cannot reach, arriving without warning, crossing the solar system, and disappearing back into the dark. They are not spacecraft. They are probably natural fragments of other planetary systems. But that may be what makes them so valuable. They are samples from alien solar systems that come to us. We cannot chase them easily. We cannot retrieve them. We may barely have time to study them. But Rubin may be the telescope that catches them before they vanish. Visitors we never invited. Messengers from stars we may never see up close. A supernova is one of the most violent events in the universe. A massive star reaches the end of its life, collapses, and explodes outward with enough power to briefly outshine entire galaxies. For astronomers, supernovae are cosmic beacons. They are bright. They are dramatic. They announce themselves across the universe. But there is something stranger than a star exploding. A star that simply disappears. This is called a failed supernova. Instead of blasting its outer layers into space, the star collapses directly into a black hole. No brilliant explosion. No spectacular light show. No warning flare bright enough to dominate the sky. One moment the star is there, then it is gone. For decades, scientists have theorized that failed supernovas should exist. But catching one is extremely difficult because the entire event is defined by absence. You are not looking for something that appears. You are looking for something that vanishes. That is exactly the kind of mystery Rubin was built to find. Because Rubin watches the sky repeatedly, it can compare what was there before with what is there now. If a star fades, disappears, or changes in a strange way, Rubin can flag it. And in early data, astronomers found a candidate in the Andromeda Galaxy about 2.5 million light-years away. A star that may have stopped existing. If confirmed, it could be one of the most important discoveries in stellar death. Direct evidence of a massive star collapsing quietly into a black hole. No explosion, no warning, just a silent death. That changes how we think about black holes. Because if some massive stars collapse without bright supernova, then there may be more black holes forming silently across the universe than we realize. Stars may be dying in the dark. Entire black holes may be born without announcement. And until now, we may have missed most of them. This is the kind of impossible thing Rubin captures. Not because it looks deeper than every telescope, but because it watches differently. It sees change. It sees absence. It sees motion. It sees the universe editing itself in real time. And behind all of this is the biggest mystery Rubin was designed to explore. The invisible universe. Everything we can see, every star, planet, galaxy, nebula, asteroid, and human body, makes up only a small fraction of what exists. Dark matter and dark energy dominate the cosmos, yet we still do not know what they are. Rubin will map dark matter by measuring how invisible mass bends the light from distant galaxies. For the first time, we may begin to see where the unseen structure of the universe actually lives. A map of invisible mass, a map of cosmic acceleration, a map of the forces shaping reality from behind the curtain. And if Rubin's first months have already shown us impossible asteroids, hidden stellar rivers, silent stellar deaths, and visitors from other stars, then the question is terrifying. What happens when it truly begins watching the entire sky? So, what did the Vera Rubin telescope really capture? It did not capture one impossible thing. It captured a universe that refuses to stay still. For thousands of years, we looked at the night sky and thought we were seeing something permanent. Stars fixed in place, galaxies frozen in the distance, constellations that seemed eternal. A universe so vast and slow that human lifetimes were too short to notice its motion. But Rubin is proving that this was never true. The sky is changing constantly, every night, every hour, every moment. Asteroids drift through the solar system. Interstellar objects pass through our neighborhood without warning. Galaxies tear apart smaller galaxies and leave rivers of stars behind. Massive stars may collapse without exploding. Hidden black holes may be born in silence. And invisible matter may be shaping everything we can see. Rubin did not just give us a sharper telescope. It gave the sky a memory. That is the revolution. Because when the same sky is photographed again and again, the universe starts to reveal its secrets through change. A moving dot becomes an asteroid. A missing star becomes a possible failed supernova. A faint stream becomes evidence of galactic violence. A tiny distortion becomes a clue to dark matter. And once you begin comparing the sky to itself, the cosmos stops looking like a picture. It becomes a living system. The first images were already overwhelming. 10 million galaxies in one photograph. A number so large that even the mind struggles to treat it as real. Each galaxy a world of billions of stars, each star a possible system, each system a possible history. And yet that single image represented only a tiny fraction of what Rubin will eventually observe. That alone would have been enough to make it historic. But buried inside the early data was something even more important. The unexpected. A stellar stream stretching 163,000 light-years from Messier 61, larger than the Milky Way itself, hiding in plain sight until Rubin revealed it. More than 11,000 new asteroids before the full mission had even begun. A massive object spinning so fast that it should have torn itself apart, yet somehow remaining intact. Interstellar visitors crossing through the solar system, fragments from other star systems briefly entering our reach before vanishing forever. And perhaps most haunting of all, a candidate in Andromeda for a star that may have collapsed directly into a black hole without the dramatic explosion we expected. A star that did not die with fire, a star that simply disappeared. That may be the most disturbing kind of discovery Rubin can make. Not the appearance of something bright, but the absence of something that used to be there, because absence can be evidence. A missing star can reveal a black hole. A distorted galaxy can reveal invisible mass. A moving point can reveal a hidden asteroid. A faint stream can reveal a destroyed system. Rubin is teaching us that the universe leaves clues not only in what shines, but in what changes, moves, fades, bends, or vanishes. And that changes everything. Because until now, much of astronomy depended on where we happen to look and when we happen to look there. But Rubin is different. It watches wide. It watches repeatedly. It watches with speed. It watches with memory. Every few nights it returns to the sky and asks the same question. What is different now? That simple question may become one of the most powerful tools in the history of science. It may help us find asteroids before they become dangerous. It may reveal interstellar objects early enough to study them properly. It may catch failed supernovae as stars collapse into black holes. It may uncover hidden streams around galaxies, showing how cosmic structures grow by consuming one another. And it may help map dark matter, the invisible substance that holds galaxies together, bends light, and dominates the architecture of the universe. That is the deepest layer of this story. Rubin was named after Vera Rubin, the astronomer whose work helped prove that galaxies contain far more mass than we can see. Now the observatory carrying her name may create one of the greatest maps of invisible matter ever made. A map not of stars, not of planets, not of glowing gas, but of the unseen skeleton beneath the cosmos, the gravitational framework holding galaxies together, the hidden structure guiding the evolution of the universe, the part of reality that has shaped everything while remaining invisible. And then there is dark energy, the unknown force driving the accelerated expansion of space itself. We do not know what it is. We do not know where it comes from. We do not know whether it will continue forever. But Rubin may help measure its effects across billions of galaxies and billions of years of cosmic history. That means the telescope is not only watching asteroids, stars, and galaxies. It is watching the fate of the universe. And this is why the first discoveries feel so unsettling, because Rubin has barely begun. The full survey has not even shown its true power yet. And already we are seeing objects that were not in any catalog, structures larger than galaxies, asteroids that challenge physics, possible silent stellar deaths, and visitors from beyond the sun. So what happens when Rubin has watched the sky for 1 year, 5 years, 10 years? How many impossible objects are waiting in the data? How many stars will vanish? How many black holes will be born without light? How many interstellar visitors have passed through our solar system without anyone noticing? How much of the universe has been moving, changing, and collapsing while we believed it was still? That is the terrifying beauty of Rubin. It does not make the universe feel smaller. It makes it feel more alive, more unstable, more unfinished. For centuries, humanity stared upward and saw silence. Now Rubin is watching the silence move. And the impossible thing it captured may not be one asteroid, one star, one galaxy, or one object from another system. The impossible thing may be the truth itself. The universe is changing all the time, and we have only just built a machine capable of noticing.